Hello everyone! In this video, we are going to talk about the t-test and what we need to think about when we run one. For it is easy to do stats to produce a p-value, especially with Prism, but it is difficult to do good stats, as in stats we can believe to actually quantify how much we can trust what our data are telling us. In a nutshell, we use a student t-test when we want to know if there is a significant difference between the means of two groups of values. But what does it mean significant? It has to do with the p-value, right? But what does the p-value actually mean? And can we use it on whatever data? If not, how can we check our data are okay? And how does the t-test work, by the way? And is there only one type of t-test? Okay, that's a lot of questions. Let's start from the beginning. The t-test is a super friendly test, which, as we just saw, compares two groups of values. Now, we are not talking about any values. First, the t-test actually compares the means of two groups of values. So our data need to be quantitative. Second, we are not talking about any quantitative data. We want ours to be well behaved, or more specifically, we want them to meet certain assumptions. And we want that because the t-test belongs to the parametric family. It means it is happy to deal with data which show normality and homogeneity of variance, which are the assumptions I was talking about, by the way. I explain more about assumptions for parametric tests in the video on data exploration, which is an important complement to this one. When it comes to statistics, which are pretty scary for a lot of us, it is super important to remember what it is that we are actually doing and the thought process we should stick to. So first, we need to remember it is all about statistical inference. We look at a sample and we are going to use what that sample tells us to infer to the general population. So it is really important that this sample is a good representation of what is actually happening in the population from which it is taken. It is also important that this sample is big enough, and we talked about it in the video on power analysis. Second, we should be led by the biology or the scientific question in a wider sense. So, we run an experiment or make an observation and say we see a difference. The first question should be, is it meaningful? As in exciting enough that it is worth exploring further? If the answer is yes, then we want to know if it is real, as in if it is likely to be true in general. For that, we use statistical tests. And most statistical tests produce a statistical value. Like the t-value, for instance, for the t-test, which is the combination of the actual difference, the noise, so the variability in the data, and the sample size, on which we base the confidence we have in what we see. That statistic t is compared to a critical value, and if it is bigger than it, we reach significance. We talk about this critical value business in the video on power analysis. Now, stats are all about understanding and controlling variation. So to do that, difference and noise are combined into a ratio, often referred to as the signal-to-noise ratio. Many parametric statistical tests, such as the t-test, are a variation on the theme of that ratio, which we want big, right? A big difference between the groups of values and very little variability in it, so that we can discriminate between them. Okay, so it comes from physics, and these guys say that if the noise is low, then the signal is detectable, and bingo, for us it is statistical significance. But if the noise, for example, the inter-individual variability is high, then the same signal will not be detected and we don't reach statistical significance. And the t-test is exactly about that. Say we want to compare two groups of values. The problem is that people often focus on the absolute difference and forget about the variability in the data. One of the reasons for that is because many people still use bar charts to represent their data, and these can be very misleading as we cannot see how the data are behaving. I must say I really dislike bar charts, and it is a good thing they are getting out of fashion. Variability in statistics is as important as the difference. So, for instance, here we can see the signal or absolute difference in our case and the variability in the data. Now, if we look at this graph and we try to guess the likelihood of a significant difference between the two groups, we are probably going to be a bit unsure. There is something going on, all right, but would it be significant? Not so sure. Now, if we look at this second graph, same absolute difference and same sample size, there is no way here that we reach significance. No way we could discriminate between the groups. And if we look now at the third graph, again, same absolute difference and same sample size. Here, yes, we will get a significant result. So variability does matter. Now, as I said, the t-test is exactly about the ratio between signal and noise. For at the numerator, we have the absolute difference, and at the denominator, we have the variability. So we get a statistic t, and the bigger it is, the smaller our p-value will be. Now, let's try an example. We are going to compare the body length of coyotes between sexes, and why not? And if you've watched the video on data exploration, which I really recommend you do, you know I like these guys. Now, before doing any stats, the first thing is always to get to know our data, to explore them. There are 3 graphical representations which are super informative when it comes to data exploration. Scatter plots, which tell us about symmetry and homogeneity of variance, and box and whiskers plots, which tell us about symmetry and homogeneity of variance as well, but also allow for the identification of outliers. By the way, we should never be too hasty and throw away outliers. And once more, I explain more in the video on data exploration. And finally, Prism has a cool new feature, violin plots. They can be very powerful tools to explore data behavior. These 3 graphs give us a very good look at the data. If we think normality and homogeneity of variance, we can see we are okay. If we want another reassurance about normality, we can use formal tests. Prism offers 4 of them and a QQ plot, which is yet another way to check the first assumption. I explain more about it in the video on data exploration. Have I mentioned it is an important complement to this one? Here we get the test results, and non-surprisingly, they all agree that the coyote data are okay, as in their distribution does not appear to depart from normality. So let's move on to the t-test. The thing is, there are several flavors of t-test. The first 2 flavors are unpaired, the default, or paired. This is really about design, and it is the first thing Prism wants to know. So in our case, we have 2 groups of coyotes, and for each group, a bunch of values which are independent from one another. So each coyote produces one value, its length. This is clearly unpaired design. A paired design, which would mean the use of a paired t-test, would be if, for instance, we had caught young male coyotes, measured their length, and then came back to catch and measure the same coyotes, say a few months later. The question would then become, have they significantly grown in that period of time? Each coyote produces 2 length values. That's a paired design. Then, one last thing, we think about normality and homogeneity of variance. T-tests are either 2-tailed, the default, or 1-tailed. Before we talk about tails, let's remember that in stats, the null hypothesis is that there is no difference. And statistical tests are here to tell us if we can reject that null hypothesis or not. So, for our coyotes, the null hypothesis would be no difference between males and females. Now, the tails in question are the ones of the distribution of the differences. And since we are under the null hypothesis that there is no difference, the distribution centers on 0. Now, the bigger the difference, the more likely we are to get a significant result right. So, back to the tails. It is really about the question we are asking. If we ask, is there a difference? That difference can be positive or negative. And the 5% area, as in p-value below 0.05, is split into 2 areas, which each represents 2.5% of the values. If we ask a question like, is it smaller or bigger than? Then the significant area is all on one side, hence one tail. The choice between 1 or 2 tails needs to match the scientific question, so has to be made at the experimental design stage, way before collecting the data. In our case, we want to know if there is a significant difference between males and females, so we go for the default 2-tailed. Finally, the t-test at last. We get a p-value, which is not significant. Prism also gives us a t-value and the degrees of freedom, about which we will talk more in another video. The f-test checks out the variances, and no surprise here, there is no significant difference in variability between the two groups. So, if males coyotes are on average longer than females, the difference is not significant. Now, one last thing. A p-value is meaningless without context. The actual observed difference is one of the things to consider. And if it seems exciting, but the p-value is not significant, then perhaps it has to do with power. Thank you for listening, and don't forget, stats don't have to be scary.